So again, it's a type 1 problem. I'm going to roll a marble off the top of a table, and the marble is going to land someplace on the ground. I'm pretty confident that we're looking at something that's going to look like that. Now, again, what makes it a type 1 problem? When the object rolls along the table, it's rolling only in the horizontal direction. So this object's going to leave the table with no vertical velocity. So as we establish what the object's going to do, we can start from there. Now, every one of these problems, I would like you to begin kind of the same way. I like to draw a picture. I think it's a good idea to draw a picture. But I also think it will be in your best interest to draw yourself a chart like I have on the right there. So I'm just going to recreate them here. And I'm going to start with vertical on this side, horizontal on this side. I'm just going to move them around because once the picture's drawn, you guys probably don't need to see that in the back, but seeing what we're going to do next probably is helpful. So let's remember all the things that are in that chart. There's delta y, there's vy initial, there's vy final, there's acceleration, and there's time. And yeah, every single problem, I'm going to rewrite this out. It's not because I don't believe in you guys. I'm helping you because I won't have that chart for your quiz on Monday. And yes, Monday quiz. I'm giving you many days notice because you said I don't give enough notice. So Monday's going to be it. First 10 minutes of class, I'm going to ask you to do one of these. Now, coming up with that chart right off the top of your head should be something that you can do pretty easily. But remember, all of these are vectors. So we have to consider positive and negative for all of those. So let's first identify the information that has been given in the problem. And remember what we're shooting for, at least 3 pieces of information on this side or 2 pieces on this side because we're trying to link together the times. So, do we know the vertical change in position of the object? Yes, 0.75. Excellent. It's going to land 0.75 meters below where it starts. Do we know the initial vertical velocity of the object? Yeah, it's 0. Type 1 problems will always have a 0 there. And anytime we can introduce a 0, that's better. Do we know the final velocity of the projectile? Do we know how fast it's going just before it hits the ground? No. Do we know what is pulling the object down? Yeah, gravity, so 10. And I think it's pretty clear we don't know how long it's in the air. So let's move over to the horizontal side because there's more things to ask. Do we know where along the ground the object lands? No, that's actually the question mark. Where is it going to land? Do we know how fast it's traveling sideways? 2 meters per second. Excellent. All right, lots of information there. So let's remember that before we start our problem, we have to identify whether up is going to be positive or negative, and now because it's 2-dimensional, also to whether the right is positive or negative. So what would you like? Do you want up to be positive or up to be negative? All right, if up is positive, then to the right, do you want that positive or negative? These are things I'm looking for when I check your work. Did you make a reasonable attempt to make this decision? Now, anything that's up gets a positive, and anything that's down gets a negative, so it lands below where it started, so that's negative. And it's pulled downwards by gravity, so that gets a negative. And anything to the right gets a positive, so I put a positive there. Now, it's clear to me that we have 3 pieces of information in the vertical side. Do you guys see that? So we need to figure out how long it's in the air. We're going to be using one of the Galilean motion equations to do so. So I think let's pick one that's going to work. And I'm kind of steering you towards the one I think is going to work there. I think we'll do delta y equals 1/2 a t squared plus vy initial times t. That has everything in it except for time. So negative 0.75 equals 1/2 times negative 10 t squared plus 0 times t. Now punching the buttons in is your next step. you should do that and find out how long it's in the air. But we have done that an awful lot. So it's going to be 0.39. Punching the buttons in the calculator is the least interesting part of this. You guys know that, right? Once you figure out the time, you're going to use it in two places. That gives us a chance to figure out where along the ground it lands, and that's delta x equals Vx times t, or 2 times 0.39, which tells us it lands 0.77 meters away from the edge of the table. What's that? 0.78? I believe you. Do you guys see this? Not hard? Any questions about what we just did? Now, they're always pretty straightforward, and Mr. Shelton does it. So we're going to change up the problem, and I'm going to leave this one to you. What if instead you were hoping to hit a spot that was 1 meter away from the edge of the table? You can't change the height of the table, but you could change how fast you roll the marble. How fast would you have to roll the marble in order for it to land 1 meter away from the edge of the table? Your process to do this is almost identical. I want you to give it a try. I'll say it all again. I want to land 1 meter away from the edge of the table. So how fast would I have to roll the marble in order to land 1 meter away from the table? Give it a try. All right. Is that enough time? There wasn't a whole lot to do. I assume you used Vy final squared minus Vy initial squared equals 2a delta y. This would do it, right? And you'll have Vy final squared equals 2 times negative 10 times negative 0.75 to give you Vy final. What'd you get? 1.8? Sorry. 3.8. So it would have been plus or minus 3.8 meters per second, but which one do you choose? Minus, because it's downwards. Everybody good? Now, I'll remind you about something that we're supposed to also be studying at the same time, and that is vectors. Can I move on, or are you guys still working this out? Because I want to move on. That means at the moment it reaches the ground, it has two components of its velocity. Again, trying to use the vocabulary. One of the components of the velocity is the horizontal velocity, which you just found to be 2.56. The other component of the velocity is the vertical velocity, which you just found to be 3.8, and it's downward. Oh, come on. Help me out. Michelle's going to lash out irrationally. There. Everybody follow along with this process so far? So another thing that could be asked of you, what angle is it traveling when it hits the ground? Or what is the total speed of the object? These are two other questions. Total speed or the angle it strikes the ground. Now, our information is all separate. All the work we do is either horizontal or vertical, but this problem isn't asking about that. It's asking about the total velocity when it reaches the ground, which, if we place these tip to tail, it's asking about this velocity. So, do you see a clearly implied triangle here? This angle will be the angle that it strikes the ground. And this arrow, which you probably get from Pythagorean theorem, will be the total speed that it strikes the ground. So when asked to find the total speed, you need Vy final and you need Vx. You're going to use trig here. And you can use either trig or the Pythagorean theorem here. All good? Do you guys kind of see what you're going to be expected to do? I don't want to spend the time watching you push the buttons. You understand that that's the least interesting thing. But we're talking about doing the square root of 2.56 squared plus 3.8 squared. That'll be that total speed. And if I label my triangle right, this is the opposite side, this is the adjacent side. Looks to me like we're looking at tangent of theta, which would be 3.8 over 2.56. That looks like how we get the angle. You guys following along all right? All little pieces to this. All right, we're going to go on to a new example. Because my hope is to give you a whole bunch of examples. This one's going to probably take the rest of the class. There's not much time left anyways, but I want to see if we can at least get through this example. I called this a type 2 problem yesterday. I'm going to exaggerate the arrows a little bit, but we're going to hit the object at an angle, and the object's going to travel something like that. Now, I hope you recognize that in order for us to use the chart on the right, we're going to need to figure out what the object's horizontal velocity is and what its vertical velocity is. So we'll have to be given something like the launch velocity, and I'm going to use V naught as that symbol, but it represents the launch velocity, and we'll have to be given a launch angle, which we'll just call theta. Now, zooming in on just this for a minute. At the moment it's launched, there will be a horizontal velocity and a vertical velocity. Now these two velocities, they are components of the velocity. They represent the components. V naught is the actual velocity. But we have to break that velocity up into the part of that velocity that's in the vertical direction and the part of that velocity that's in the horizontal direction. So that's what we're doing here. We're going to break it up so that we can use it to study our problem. Do you kind of see an implied triangle? All right, good. So to me, that implied triangle looks like that. That good for you guys? That makes this the opposite side and this the adjacent side. If I use my trig, then sine of theta is going to be the opposite side, Vy initial, divided by the adjacent side, V naught. Now, I think I can solve for the initial velocity here, right? Multiply both sides by v naught, and that says that vy initial is v naught sine of theta. Let's move on to cosine. Cosine of theta equals adjacent Vx divided by hypotenuse V naught. Again, I think I can solve this for the horizontal velocity. So Vx equals V naught cosine theta. Now, look, I don't like giving you stuff that you can just memorize because it feels cheap. But if the angle is always compared to the horizontal, that will always be true. So let's consider an object that is launched at 2 meters per second and an angle of 30 degrees. Let's see where it lands. Now, this is a type 2 problem because there is something that's a 0 in this problem. So again, I like to give them names, and this one's type 2. What's our 0 in this problem? The y displacement will be 0. It lands at the same height that it was launched. So although part of this problem got a little more complicated, part of this problem definitely got easier. What's wrong? Making me mad. So I'm going to get my little chart out again. Vertical, horizontal, delta y, vy initial, which now we know is always v naught sine theta, vy final, a and t, and delta x, vx, which we now know is always v naught cosine theta, and t. Do you guys want up to be positive or down to be positive? Up is positive. Do you want the right to be positive or the right to be negative? All right. It seems like this is something you guys can do. Put the picture on the bottom. Put this over here on the top. Let's see what we can put together here. Delta y is going to be what? 0. That's right. Type 2 problem. Delta y is 0. Now, we do need to figure out v naught sine theta. That's going to be 2 times the sine of 30. So you can put that into your calculator, figure it out. It will be 1 meter per second, and it's upwards, so it's positive. Moving along, do we know anything else in this list of things? Acceleration, yep, 10 meters per second squared. And it is directed downwards, so I make it negative. Do we know delta x yet? No, so we don't know. In fact, that's what we're looking for. Do we know the horizontal velocity? You may not know it, but you can figure it out, right? It's got to be 2 times the cosine of 30. So I get 1.7. You should keep some decimal places here. So 1.732 meters per second. Do you have enough information to figure out the time on one side or the other? Yeah, I think we can. So delta y equals delta y equals 1/2 a t squared plus vy initial times t. Be careful with this one. I want to show you something, which is why I'm spending so much time on these. There's actually 2 answers for the time. Technically, the way I'm supposed to do this is factor out a t and set both of those equal to 0. And I find one of my answers is 0, and one of my answers is 0.2 seconds. be careful. I want you to be thoughtful. When we asked when was the object on the ground, there was 2 times that it was on the ground, right? At the beginning, t equals 0, and at the end, 0.2 seconds. Not a big deal, but this is the way math works, and I like to make sure we understand that math works. But that just means 0.2 here and 0.2 here. Now, not particularly hard, right? I want to find out where it lands. Looks like delta x is going to be 1.732 times 0.2. So over here, 0.35 meters away. Any questions yet? All right, here's a common part B. Is it pretty clear that somewhere over here it's going to reach its maximum height? Okay. If you're asked what the maximum height is, that is a completely different problem. Because we're not talking about being over here, we're talking about being here. So if the question asks for the maximum height, you need to change the information in your chart. So let's say the next question is, what is the maximum height? Well, none of this that we've figured out for where it lands is going to be necessary. The initial stuff will be necessary, but it's no longer landing, so this delta y is not going to be 0. In fact, if you're asked for the maximum height, you're being asked to find delta y. But if you're being asked for the maximum height, you do have to kind of reboot your problem a bit. But note that maximum height occurs when the final velocity is 0. We're talking about the y velocity only. It's still moving sideways at 1.732 meters per second. But at this point, it's at its maximum height. So do you guys see the next thing that'll be? Just Vy final squared, Vy initial squared, 2a delta y. You guys see that that's going to be our next step, our next thing to do? But remember, it's a different question because we're talking about halfway through the motion, not the whole motion. All right.